Well, it's time to look at the second derivative again and what the point of inflection is. We're also going to be looking at some other derivative rules. We're going beyond just multiplying, dividing, subtracting and adding. We're looking at exponential and logarithmic derivatives. It's going to be a fun episode. Okay, so the second derivative. Second derivative just means you actually differentiate twice. So, let's say I had x squared as my function. A nice parabola. Well, that's my f of x. The f prime of x is my first derivative. This is the slope that represents any given point on the function x squared. So when we differentiate this, we get 2x using the power rule, because we subtract 1 from the power and we bring the exponent down into the position of the coefficient. From there, we simply need to find the f prime prime of x. And if we have any function, where if it's regardless of what the actual coefficient is, but if it's just a coefficient and x on itself, not raised to any power, then the derivative of that is just the coefficient. So the second derivative is equal to 2. This means that if we were to actually look at these functions here, we have x squared, which would be this one here, and then we have the f prime of x, which is 2x. We have a linear equation, and then eventually we would have just a flat line representing the slope. Because here the slope is static, here the slope changes a bit, and essentially you decrease by a degree each time you go through the process. But we want to do more with the second derivative than just actually differentiate twice and have a look at this. We need to actually have some context there to guide why we would want to do that, why we would want to inquire into that. And so, my friends, that brings us to finding the second derivative to gain a point of inflection value. So consider the function f of x equals x squared plus 4x plus 6. Let's say we wanted to know the points of inflection on this function. Well, we would differentiate once to get 2x plus 4. And then we would differentiate once again to get 2. What does this actually tell us about the function x squared plus 4x plus 6? We've got to set the second derivative to 0 in order to solve for the point of inflection. So what this is actually telling us when we get a result like this, that's just a constant, is that we can't actually find a horizontal point of inflection because 0 does not equal 2, so we can't set the second derivative to 0. And what does this tell us in context? Well, it tells us that if we just had a parabola like that, there are no points of inflection. Why? Because the entire thing is convexing. There's no change between concave and convex. There's no point that actually changes between the two because it's just a parabola. So you need a higher order degree polynomial in order to actually have this work. So, let's actually try again. Let's have a look at a cubic this time. And in order to do this, I'm actually just going to expand on what we have and add another term. So now let's take the first derivative, 9x squared, because we multiplied the exponent and the coefficient to get 9, and then we subtract 1 from the exponent. We do the same thing here, so we get 2x plus 4. And now we've got something that we can actually solve for an inflection point because it's not just a constant. The derivative of the first derivative is actually going to result in some x value being present, meaning that we can solve for 0. And when you think about it, it's not just a parabola, we've got a more complex shape, so there'll be some changes between concaving and convexing. Just to note, that isn't actually the function, but it shows you that we can find a point of inflection because we actually have that change, whereas with a parabola we don't have that change. So, we differentiate again using the power rule. And hence, we bring the 2 down, so we get 18x plus 2 as being the second derivative. And we can solve for 0. So, what this means is 0 equals 18x plus 2. Because when the second derivative is 0, that's that point of inflection, that change from concave to convex. Again, if you need help remembering, concave looks like that, and convex looks like that in terms of a function. And when you have a higher order polynomial, say a cubic or higher, or a quintic or a quartic, then you'll have changes between them all the time. And when the second derivative equals 0, that's when we're going to have this. And the reason that is because if we consider the first derivative of the function, then it's going to be 0 when we actually have that. So when we consider the inflection points of the second derivative, it's going to be, the inflection points of the original derivative is going to be linked to the second derivative equaling 0. So in order to solve this, we bring 2 to the other side, so we just have 18x, and it's going to be negative 2 because we inverse the operation. And it's going to be negative 2 on 18 equals x, because again it's 18 times x here, so we need to swap it from the numerator to the denominator. And as a result, this gives us a coordinate point where the function changes from concaving to convexing or convexing to concaving. And we can actually find out whether it goes from concaving to convexing or convexing to concaving using what's known as a sign diagram. So, what we do is simple. We plug in values less than negative 2 on 18 and values greater than negative 2 on 18. It's as simple as that. Try and pick ones that are easy for the arithmetic to do. So, we plug them into the function f prime prime of x, and what we get here is we get 18 lots of, and let's go with negative 1 for example. 18 lots of negative 1 plus 2 equals, and we got negative 18 plus 2, which is negative 16. So that's the f prime of negative 1. If we look at the f prime of 1, or should I say f prime prime, sorry, for the second derivative, then it will be 18 lots of 1 plus 2, which is going to be equal to 20. What this is telling us is that we actually have a negative second derivative before this point of inflection, and a positive second derivative after this point of inflection. So as a result, we can actually determine whether it's concaving or convexing. And there's an easy way to actually decipher this, a little analogous thing that may be able to help you. A frowny face and a happy face. How does this link to the second derivative? Well, if we end up with a negative result, like we did here, then that means that the function is concaving. Because we have a negative face, he's frowning, he's not very happy, he's negative, he's sad. But if we have a positive, happy second derivative, that means that the function convexes from that point. It's as simple as that to remember. So when I'm saying the function, I'm referring to the original f of x. So I'm saying that that function there, we have this value where it actually changes from positive to negative, but it means that because the results before that value are negative, it means that it is concaving, and then because the results after that are positive, it means that it is then convexing. And just remember to use those terms. Negative means concaving, positive means convexing, and you can get it by either a frown or a smile. And when we draw the sign diagram, which can be very helpful for just annotating this principle, then what we do is we show the x-coordinate of the horizontal inflection point, and then we just simply do a negative to the left of it, and a positive to the right. And again, it means concaving and convexing in context. That inflection point is that change from concaving to convexing. Okay, so that's how we look at the second derivative. We simply differentiate twice and set it to 0, just like we did when we were trying to find stationary points for our original function f of x by using the first derivative. Again, similar principle, but just using the second derivative this time. It's based on curve properties. If you really want to, I'd recommend going away and looking at some of the proofs behind why the inflection point of the function f of x can actually be found by setting the second derivative to 0. It can be some very interesting maths if you're interested in inquiring a little further. But now, as I promised at the beginning of the video, we're going to look at exponents and logarithms and their derivatives. And we're just going to focus on a few basic ones today. They're quite easy to grasp, but let's go through this anyway. And I'm going to start off with probably one of my favourite derivatives. This one is really magical, and this one can probe a lot more questions as well. The function e to the x and its derivative. And if you want, I really recommend taking away from this session or just sort of thinking about just how cool this is, and maybe even going to look at some proof for this, because it is quite an interesting concept. But if we have to find the derivative of e to the x, so the f prime of e to the x, then it's actually itself e to the x. And that's what's amazing about Euler's constant raised to the power of x. It's its own derivative, and when you get to integral calculus, it's its own antiderivative as well as a result, which is it is amazing. It's the only function that is its own derivative and its own antiderivative. So what does this actually mean? Well, we know that the first derivative means that we're looking at the slope. Well, it means that if we have the function f of x is equal to e to the x, then at any point along that curve, the rate of change is going to be e to the x. That's the difference in y relative to the difference in x. E to the x is its own derivative because of that. And it's pretty cool. It is something worth investigating further if you are interested in maths. But there's the first rule, probably the simplest differentiation rule. If you need to differentiate e to the x, just rewrite it, you're done. But now, what if you need to differentiate e to the f of x? This is where it gets a little bit more complicated, but it's still not that difficult. So what do I mean by e to the f of x? Well, e to the f of x could, for example, be e to the 2x plus 2. Something like that. So, if we wanted to actually solve the derivative of this, we just need to have e to the f of x, you rewrite it as is, and then you just take the f prime of x. So you actually take the derivative of what the e is raised to, the power that e is raised to. So in order to do this, let's say we have e to, I'll just use my example here, we want to find the slope of the function e to the 2x plus 2. Again, it's always cool to graph these functions on your calculator, and I just want to point out that e and natural log are really things you come across a lot, especially in nature and all around the place. They're really cool constants. It's more often that you'll probably get these sorts of results when you're actually collecting data and analysing trends and numbers all around you than actually getting pure polynomials. Just because the world's a little bit more chaotic. These are just some special constants, but you may even get something much more advanced than this as well. But when we actually differentiate that, we just rewrite it, because we just rewrite it as e to the f of x, which is itself in its general form. And then we actually just take the derivative of this. And we know that's 2x to the 1 there, so we bring the 1 down to the front, and 2 times 1 is 2, and then it's x, and then we actually subtract 1 from the exponent, so it's 2x to the power of 0, and anything raised to the power of 0 is just 1. So it means that f prime of x, so just the derivative of that tiny bit there, in fact, just to make the notation a bit easier, I might even make that g prime as well, but if we have the g prime of e to the f of x, then we can actually rewrite it as just 2e to the 2x plus 2. Again, it's just the function rewritten, and then it's the derivative of the exponent term. And those are our basic e to the x and e to the f of x rules. And you can use them with quotient rule, you can use them with sum rule, you can use them with all those other rules you've already learned. So you can mix them in with your polynomials now. Again, these do require a bit of practice. Not really this one though, but again, it's just using stuff you already know, but applying it to new constants and new fun situations. So now you can look at things like nature and numbers and all of that great stuff as well. But now let's have a look at some of the ln derivatives, and that'll be the finish up to the video, so I'll just go through this quickly. And these ones are probably a little bit more difficult, but ln is the natural log. So imagine if we have, it's basically log in base e ln. They're inverse of each other. So, if we have, say, we want to find the derivative of ln x, then the answer is just 1 on x. And this is another one like e to the x. I won't go too much into explaining why that is the case. It's just a special property of e to the x. So when we think about it, they're inverses, and that's something you can take away from this lesson when you might try to actually explore it a little bit further. But when we have the derivative of ln x, it's just going to be 1 over x. It's really that simple, and you're able to use it with other terms as well. But if we want to find the derivative, let's say we had a function g of x, and that function included ln f of x, whoops, then what we actually need to do is we need to have the f primed of x over the f of x. So it's really quite simple here. So we have the natural log, and then we have those modular symbols, which simply mean we generally look at the true value of ln. And from there, what we actually do is we just say, okay, what's within the modular symbols? Just differentiate it, and then rewrite it over the normal function itself. So again, this one's only limited just to ln x, so if you just need to differentiate ln x, you do that. But if you actually have like an f of x in there, say for example, x squared plus x to the 3 plus 4x to the 4 plus 5x plus 3, for example, then you could differentiate that. And I'll actually do that example now, just to go through the process with you. So we want to, so let's say our g of x is equal to x squared plus x to the 3 plus 4x to the 4 plus 5x plus 3. Then what we do is, in fact, I'll just go ln there and put the modular symbols around it. But what we actually do is we say, well, okay, this can be our f of x, because it's what's within the modular symbols. So I just need to differentiate that and then write it over the function as it is. So we get the g primed of x, again, because there's an ln out the front, we can just use that law. And we end up with 2x plus 3x squared. Again, you can feel free just to use the power rule. The power rule comes back to many of these laws that you already know as well, especially with the examples I'm giving. In the last video we'll have a few more complex ones, but again, you should be able to differentiate these quite quickly now. Again, you just bring down the exponent, multiply by a coefficient, and then subtract 1 from the power. And then you rewrite it over the original function. And guess what? You've actually just differentiated something with ln, the natural log. that's all for this video. I really recommend practicing those last ones, the exponents and logarithm ones, also as natural log ones, because they do come in handy, and they are actually differentiation laws that generally represent the real world a little bit more, rather than just having polynomials as well. So that's all for this video. In the next video we're going to be looking at implicit differentiation, which is another mind-bending concept, but just practice these, go through them, use Formulae as your reference app, and you should be okay with that. So thank you very much for watching, and I'll see you next time.